just realized I was muted. Hello, everyone. Welcome to Global Hack Week, specifically my stream on supervised learning using Python. This is a good start to machine learning, just kind of diving into a specific yet foundational concept in machine learning. We'll be using Python and Google Colab to kind of walk through everything today. But before we get started with all the meat, I'd like to know how your Global Hack Week is going. Have you been enjoying yourself? Any cool streams you've seen throughout the week? I'd love to hear about it. Awesome. Looks like we have a few people in the chat. I'm glad you're all here. A little bit of an agenda of what we'll be doing today throughout the stream. First, we'll have kind of an introduction to machine learning, an introduction to kind of the mechanics of the stream. And then after that, I'll dive into kind of the basics of supervised learning and the conceptual pieces behind what we'll be coding up today. And then we'll be moving into the installation aspect, how we can get our Google Colab sheets configured, and moving through any errors or hiccups you might have with that. It should be a relatively quick process compared to installing everything on the desktop, but I want to make sure that y'all are kind of having that support and everything is working from the get-go. And after that, we'll dive into kind of exploring the data set we'll be working with and then building our supervised learning model. Awesome. So now that we kind of went through the structure, a little bit of an introduction. My name's Gabriella. I'm a coach here at Major League Hacking. My background in machine learning is relatively new, but I'm starting to work on some machine learning research with the Spot robot dog from a university, which is a lot of fun. And kind of outside of work and school, I've recently gotten back into reading, which has been a lot of fun. I kind of got out of the habit of reading books throughout college, and it's been great to kind of dive back into that. If you're looking to go through the slides after this presentation or kind of to keep along throughout this presentation, you can head to this bit.ly. It's bit.ly/GHW213, and you'll be able to find my slides. It looks like we have a hacker who is a little bit sleep deprived because of different time zones, but is excited because of different interesting sessions. Love to hear it. Someone else is on time to a stream. Love to hear it. Okay. And I'm doing pretty well myself. I'm excited to do my first stream of this Global Hack Week. So kind of diving into like what machine learning is. If you're new to machine learning as a concept, or this is your first stream, you just kind of popped on here. Machine learning is essentially a subset of artificial intelligence that allows a system to kind of like learn on its own, and it improves learning different neural networks. It also improves learning deep learning, using deep learning, and it allows it's able to do this without being explicitly programmed to do. It makes improvements just by finding those inferences, those patterns. And it does this by finding those patterns in large amounts of data. So kind of like giving a baby that's proficient in calculus, and this baby is a computer in this metaphor, but this it's able to recognize patterns and improve from its previous experience without being specifically told to do so. You're just giving it a lot of information, a lot of books, a lot of different problems and their solutions, and from there it finds different patterns. And if you can see right here, you can see in the corner, this is a picture of Newton inside of a computer generated by Stable Diffusion, which I thought was funny. In addition to kind of like what machine learning is like as like a general concept, there's a few different types of machine learning that you should have like a general idea about, but we won't be diving in too deeply today. So the first is supervised learning, which is where the computer is learning from labeled data. So it's given different pieces of data in addition to a label or like the key that you're looking for in addition to that. So it's able to pair the different pieces to a solution, and it's being taught a little bit more explicitly based on those sample pieces of data. And the kind of models you can build within supervised learning are classification and regression. We'll dive a little bit deeper into that in a little bit. The second kind of machine learning is unsupervised learning, which is essentially the opposite of supervised. So the computer is able to find different patterns in unlabeled data. So rather than being given like key pairs or like a data set that has the solution or the label, it's given all the different characteristics, but no label. And it's trying to find the label or those commonalities kind of like on its own. Different types of models you can build within unsupervised learning include clustering, dimensionality reduction, and a few others as well. And third type of machine learning is reinforcement learning, and this is how a computer will learn by interacting like within an environment in order to maximize the rewards. So essentially, during reinforcement learning, the computer is given a reward for certain outcomes and a punishment for others to kind of navigate through that and learn rather than through different key pairs or finding patterns. As far as, oh, looks like we have a question. Does it take a lot of time for an unsupervised model to process data as compared to supervised, or some magic in between? It depends on a few different factors. Unsupervised definitely takes more data and like a little bit more time, but for data sets where there are like less characteristics or more data, like that can affect processing time, as well as your specific model and kind of like the overall libraries and the processing power of your computer. But I'd say that supervised goes a lot quicker. As far as specifically supervised learning, we're going to dive a little bit deeper into that now, like kind of as a concept. So a little bit of a quick definition of supervised learning. Supervised learning is a type of machine learning where the algorithm is trained on a labeled data set. So it's learning from both that input data and the corresponding output labels in this like set that it's being trained on. And as you can see here, like a very common supervised learning example is so like distinguishing apples from oranges based on the characteristics. So in this supervised learning model, the computer would be fed a lot of features, which are things that we need to feed the computer. It's also sometimes known as the input variable, or X if we're talking about simple linear regression. And as you can see here, there are 3 oranges and 3 apples. They don't all look the same, but they're all oranges and they're all apples. The leaves look a little bit different. The like style of the drawing is a little bit different, but they'll have that like in common. So it's learning to recognize that pattern. For oranges specifically, it's learning to recognize that a very round, like orange colored image with a stem tends to be an orange, and a slightly round but not completely round image that's red and also has a green stem would be known as an apple. And in the beginning, when it's still learning, the stem might trip it up, and also the like shape of an apple versus an orange might trip that up as well when it's still beginning to learn. So, for example, if there's like a more rounded image of an apple that is not quite a bright red, that might confuse the model at first, but as it gains more information, it is able to learn a little bit better. The model is going to get better and be able to more easily distinguish between the apples and oranges. So as far as like what we'll be predicting in a supervised model, that's called a label. When we're working in simple linear regression, this will just be called Y. A lot of the formulas you use in math, specifically calculus, with X and Y can be applied to different aspects of machine learning. And you'll see this a lot with linear regression. Sometimes they have other names, sometimes they're just referred to as the X and Y variables in different formulas. But labels are the thing that we are predicting. In this model, it's what the computer is trying to figure out. It's what the computer is like trying to deduce from the patterns it finds in different images and different sets of information. This is also known as the output variable. And as you can see, if we fed it this apple that has eyes, it looks a little bit different from all the other apples it was fed before. It's going to deduce that it's an apple, even though it does look slightly different from those 3 apples. Of course, this is like a very simplified version of a supervised learning model, but I think you'll get the point. In this example of apples and oranges, is the color not being passed along as a feature along with the shape? So in this example of apples and oranges, the color is being passed along. I think you're questioning when I was talking about how a newer model might get confused with a more rounded or like not as vibrantly colored apple or orange, but the color is being passed along, and sometimes the hue or like how deep of a red or orange like will be kind of distinguished. But because of this second image, after it's being well trained, it's very red and it's more distinctly apple shaped than some of the other apples. As you can see, it's rounded, but it's not like a perfect circle. It has more of the quintessential like apple characteristics, which is like what would lead it to be classified as an apple rather than an orange. Does that make sense? Okay, perfect. And I was answering in like relation to what you were actually asking about, which is perfect. Okay, so that's kind of what features and labels are, and kind of like the basis of supervised learning, and the different things that go into building supervised learning models. So now we're going to dive into the applications of supervised learning, like what you can use it for, as well as like the more of the mechanics of how you go about coding it and segmenting a data set for training and testing it. So when you're creating a supervised learning model, as you want to do with most machine learning models, you want to have a larger training than a testing set. So in this particular example, you would want to segment about 80 to 90% of your data set to be for training. And as you can see in my sample diagram, we have a good amount of apples and oranges, slightly more apples than oranges. In this testing set, I think we have, let's see, 5 apples and 3 oranges. For a more ideal distribution, we would either want to have an equal amount of oranges and apples, or maybe 4 oranges for 5 apples. But this is just kind of the image I created when I was making my slides. So this blue section is called the training set. This is the majority of a data set. Like I said earlier, it can be 80 to 90 usually, depending on how large of a model and how much you want to like rigorously test it. Those percentages can change. And this is what is used to teach a computer like what patterns to find. This is like when we're initially just kind of teaching the computer like what to look out for, what like patterns or characteristics actually indicate the difference between an apple or an orange, or like whatever variable we're trying to find. The testing set is the minority of a data set. It's either 10 to 20, sometimes 25% of a data set. And this is essentially used to quiz the computer on its knowledge on what patterns it's finding and ensure that the model that we built is successful and we're going to get the output we desired. And if we go to the testing phase and we're getting a very low accuracy rating, then we're going to want to go back and adjust how we train the model. Maybe we're going to want to use a larger training set, or maybe adjust what patterns we point out when training our data set. All right, so as far as the different types of supervised learning, there are classification and regression. These are the 2 main models we'll focus on. Classification is the type of model we'll be building in just a second. Classification is where we're predicting different categories and classes. So apple versus orange, malignant versus cancerous, human versus not human, if we're using like human detection with like autonomous vehicles. I think you kind of get the point, but it's like kind of like a binary either or most of the time, but in some instances it could be multiple, but it's always like fixed categories or classes. So we'll have a set number of categories or classes that kind of like bound the decisions. So it's within a certain, I guess, like number of categories or classes that are predetermined. And these are used to kind of like select an object or house or like whatever you're looking into a particular category. Regression is predicting continuous values. So these are going to be numbers or more big things that can be like not just like one of 5 categories or something that's like an either or statement. It will be predicting like the price of a house. It'll be predicting the value of a stock. It'll be predicting like the number of feet between 2 objects, something like that. And these predictions, because they're continuous, they're making predictions by using a best fitted line through different data points. And by making that best fitted line through different data points, it's able to accurately predict things because it's finding kind of like commonalities between all the information it was fed by using those different points. All right, so here are some examples of supervised learning. So the 2 that I want to focus on are the iris flower classification model and the housing price regression model. These are kind of the 2 main examples for classification and regression. The iris flower we'll actually dive into in a second, and I will walk you through the data set, exploring the different aspects of that data set, as well as building that model. But in the iris flower classification model, we're using different biological characteristics of 3 different iris flowers. And what we'll be specifically focusing on are the length and width of petals and sepals to teach this classification model to recognize what type of iris flower is in an image. So in this case, we have 3 different types of iris flowers. We want to use the length and width of the petals and sepals to match this particular image of a flower. In some cases, we'll just be using like numeric measurements to determine what type of iris flower is in this particular image. Another example of supervised learning is a house price regression model, and this is where you use the year a house was built, the condition it's in, as well as the number of bedrooms. You can use a lot more characteristics because there's a lot more characteristics of houses and real estate in general. But this kind of like simplifies it by giving it 3 different characteristics to follow and kind of make patterns based off of. And based off of those different characteristics, we'll be teaching a model how to recognize how much a house will sell for. And of course, there's a lot of different things in real estate and other like real life problems where it's a lot more difficult to find patterns because things are constantly changing, such as like the market and interest rates for mortgages. Like 2 things I can think of that will change the price a house sells for, the number of inventory in a specific area, the geographic location. Like those are all things that can affect that. But in some instances where the market isn't fluctuating as much, this would allow you to find kind of like a good estimate of how much a house could sell for in a certain market. And I also wanted to highlight the foundations of like these 3 complex technologies below are based in supervised learning. So for example, voice recognition, where you're able to convert spoken word into text. If you've ever used Otter AI, if you've ever used Siri, these are these are applications of voice recognition, and that's based in supervised learning. So Siri, for example, was fed a ton of voice samples as well as what it should be matched with in order to kind of be able to recognize your like kind of commands, your questions, and be able to answer those. Of course, it's a lot more complicated than that, but that is the basis of that technology. Otter AI, if you're unfamiliar, is a really cool plugin you can use with video chat technology. So you're able to make transcripts a lot easier. I found it to be particularly useful when I was interviewing people for articles or write-ups. So I was able to go into these transcripts and go through and find specific highlights, specific quotes, a lot more easier than if I had to continue rewatching the interview. Another awesome technology that supervised learning is kind of the foundation of is autonomous driving. Autonomous driving has a lot of moving pieces. It's a very complex technology, but what I specifically want to focus on for how it relates to supervised learning is that autonomous driving will use object recognition, and by recognizing these different objects, it's able to ensure a safe journey. So the different objects it has to recognize are human versus not human, like I was talking about earlier. In certain, I guess, like high risk situations, autonomous driving creators need to focus on like where they want the car to swerve in order to save lives, and if it's okay hitting potentially like a mailbox versus a person, that has a lot of different outcomes. So that object recognition and that application of supervised learning is very important. Another example of supervised learning and autonomous driving is recognizing different street signs, stoplights, things of that nature. So by feeding an autonomous driving vehicle images of a stoplight, kind of like a yield light, as well as the green light to mean go, with different hues of the lights and different places, as well as kind of like shadows and lighting in different places, the light will kind of reflect and display differently, but it still needs to be able to recognize what those three different lights are properly and be able to kind of take action that is in line with that particular like object recognition. So that's also another like very important application of supervised learning and how it can kind of be pieced together with other aspects of machine learning, as well as just kind of engineering in general, to create really complex and interesting technologies. And the last interesting technology I want to focus on is medical diagnoses. This is a relatively new one, and I think it's very interesting. And this is where you're able to use machine learning to take patient data and characteristics of different diseases in order to recognize diseases in a patient, or sample sizes, or like test samples that have been submitted in different medical records. This one has, I feel like, the most, I guess, like ethical considerations, as well as it is very difficult, I guess, to implement and get approved. But it could be incredibly life-saving if like this is able to recognize different characteristics of diseases more quickly, or at like a broader scale than like healthcare professionals would be able to, just like due to like time constrictions. They wouldn't be able to diagnose like at the speed of a like highly trained model, but kind of using that medical knowledge in tandem with supervised learning could be incredibly powerful to recognize whether a tumor or the test sample is like cancerous or malignant, or looking into different characteristics or oddities in potentially blood work, which could lead to faster treatment for patients, which I think is a really cool thing, but of course needs to be heavily tested in order to not lead to like a lot of false positives in testing, and kind of like leading to unneeded treatment or over testing if it's giving a lot of false results. But I think it's really interesting. So those are the three pretty interesting technologies that use supervised learning at like the core of its technology. They use a lot of other pieces, but I think it's really interesting to kind of see like what other concepts your learning can be applied to in the future. So now I'm going to dive a little bit more into the iris flower classification. This is the model that we'll be building together. First, we're going to be diving into what the data set is, and kind of the different pieces of it. So kind of like I talked about earlier, there's different biological characteristics of different types of iris flowers that can determine like which specific type of iris flower it is. The lengths and the widths of both the petals and the sepals are part of the flower's reproductive system, which contains like how it creates the different flowers. If you can see to the right, There are the three iris flowers will be kind of determining in this machine learning model. We won't be using images of these flowers, but rather the length and width of the petals and sepals. And as you can see on the diagram, the petal is in the middle and the sepal is on the outside. There's the iris setosa, the iris versicolor, and the iris virginica. They're slightly different colors and kind of like displays, but you can see they're all three of them are iris flowers. They do have commonalities, even though they are a little bit different and can be distinguished as such. So that's why we need to have that model, because they're not so different that it's incredibly obvious, but we need to find those characteristics. So before we dive into looking at the data set and building out this model, I'm going to take a quick 2-minute intermission. So grab some water, go to the bathroom. I know I just threw a lot of information at you. Maybe go back and look through those slides. But when we get back, we'll be pulling up Google Colab and we'll be walking through this data set and building out that model. All right, I'll see y'all in 2 minutes. All right, we are back. I hope you all were able to grab some water as well. I got some water, so I'm able to not lose my voice throughout this. But now we're going to be diving into kind of that um, configuration and getting into the data exploration of this particular iris flower classification set. If you go to this bit.ly link, which I'll walk you through in a little bit, you'll have the starter Colab file I have. You will need a Google account to create this Colab file. It's a browser version of Jupyter Notebooks, if you're familiar with that technology, which allows you to run Python code as well as a few other languages in like isolated cells, which makes kind of debugging, data visualization, and making sure all your libraries are installed a little bit easier. So I'm going to quickly change how my screen sharing is set up. And then we can get started. All right, so you should be able to see my screen. I have a half screen with my stream as well as the code. I'm going to close this tab. What environment are we using to code? We're going to be coding in Google Colab, which is a version of Jupyter Notebook just in the browser. So if you go to bit.ly/iris starter, it's going to redirect you to the starter code. And here I have just kind of like some cells built out for you, a link to the data set, as well as some like different import statements. The link for this specific collab is bit.ly/iris starter. I put that in the chat, and this will redirect to this Google Colab file. So you can either make a copy of this Google Colab file and follow along with me, or at the end, you'll be able to just access this Google Colab file like at the end, like the finished product. So the first thing I'm going to do is take you to this specific data set. Which is the iris classification set. It's from the UCI machine learning data set. It was used originally for research, but has been used pretty frequently in machine learning. So there are a few different columns in this data set. There's the ID, the sepal length in centimeters, the sepal width in centimeters, the petal length in centimeters, and the petal width in centimeters, as well as the species. So you can scroll down and see a little bit more information about the CSV in detail. So you can see that each listing in the data set has an ID, as well as all these characteristics, and you're able to see it a little bit more compacted. You're able to see a little bit of statistics for like the actual values outside of like the ID, which is not going to be anything we'll be using in our model. So we can see that it's relatively well distributed, but there's still a little bit of a higher count towards the beginning of the data set for sepal length. We see something similar with sepal width. Petal length has a lot in the beginning, and it kind of tapers out to the end, a little bit of a rise around 4.5. Petal width, we just kind of see 4 general areas that are sticking out to us. We have a mean and standard deviation for all of these as well. And then for the species, there's 3 unique names. Like I said earlier, it was the different types of iris flowers. These are just the different iris species. In order to run this model correctly, you will need to download this data set. You can just click the download button and make sure you log into Kaggle. If you don't already have a Kaggle account, you can do so by just logging into Google, like logging into Kaggle via Google, and you'll be able to download it to your local machine. In the Iris Starter Kit, in order to upload this data set, you'll click on this folder here, and then you will see a folder that has sample data, and these are just kind of some sample data sets that Google will give you in Google Colab. And then if I've already uploaded my iris.csv dataset, if you need to upload your iris dataset, you can do so by clicking on this upload button, and then in your downloads folder or wherever downloads go on your computer, just select it and it should pop up here. So I'll give y'all a minute to kind of get to that point where you're able to copy the Colab set if you'd like to follow along that way with me and log into Kaggle and download that data set. Does anyone have any questions in the meantime? All right, if not, I'm going to start with our importing and getting this data set kind of connected to our Google Colab sheet. So as you can see, the comment I have for the first cell in this Google Colab file is for imports and housekeeping. As far as what I mean by housekeeping, I just essentially mean importing the data set and getting that ready for us to kind of explore and make some visualizations with. So the first thing we're going to be importing is NumPy, followed by pandas, and then matplotlib and Seaborn. These two are data visualization libraries. Pandas and NumPy are more for kind of data analysis. And then this scikit-learn library is for actually creating that machine learning model. So when you click this play button, it's going through and running every single line. And when you get that check mark, that means it was successfully run and executed. So you're able to successfully import everything. So after that, the next thing I want to do is actually get that data in here. So I'm just going to do that by saying iris data is equal to pd read csv. And then I'm going to put in iris.csv. I'm thinking that is the right directory over in this files, but we can always change that if necessary. So essentially what I'm doing in this line is using the pandas library to read the CSV into a variable. And as you can see, I'm getting an error, which means that it is not the right directory. So I think I'm just going to solve this problem by clicking on the three dots, copying the path, so I don't need to worry about going through the different directories. And then I'll copy that path. Okay, it was in the content folder. I can play this again, and as we can see, it ran successfully. So now we have the iris data being successfully read into this variable. All right, so now that we have this data set in here, the next thing I want to do is just print it out to see kind of like what's in the data set and like how it's being read into Google Colab. This allows you to have a better idea kind of what you're working with, not only like the different variables, but how you can kind of interact with them in your code. All right, so we're seeing these different variables we talked about earlier in the Kaggle website page. We have the ID, sepal length, sepal width, petal, as well as the species. It looks like the species are all kind of being read in a similar way. Rather than just having Setosa or Virginica, it's going to have iris dash and then the specific type of iris flower. So this is good to know because we're not just looking for Setosa or Virginica, which could mess up our code in the future. So now that we kind of have like a little bit of an idea of what's in our data set, I think the first order of business that I'd like to follow is I want to edit this data file by dropping our ID variable. I don't really see this as helping us at all, like throughout this process. The ID variable has it essentially serves the same purpose as the index. It's just one like it's just one larger than the index, and I don't really see like how that will be helping us find patterns on how to determine different iris flowers. So how I do that is I'm going to modify the iris data variable, and I'm going to make it equal to the iris data set, but I'm going to drop the ID, and this I'm going to set the access equal to 1. So I'm specifying that I just want to drop it from the data set. We'll set this equal. Okay, it was running correctly. It's printing. I'm going to change what I'm printing really quick. So it's just the iris data head. This will just be the first few rows of this data set. And then after I drop this one variable that I'm not seeing as particularly helpful to our model, I will then print it again. As you can see, it's been dropped from the data set. Now that's been updated. We're not working with any extraneous variables that we won't need for our model. Awesome. So now we kind of have that housekeeping out of the way. We can kind of get more acquainted with the data set, see a little bit more of what we're working with, the distribution, like the dimensions of everything. We'll be able to kind of break down the different aspects of that. So we'll move into the next data block, and this is just so we have a little bit more separation. When we start making these visualizations, you're able to see it a little bit better, and you're not getting confused by errors when your old code didn't have errors, and maybe a few areas down it does, so we're getting like less confused. The first thing I want to do to get acquainted with the data set is I'm going to print just the dimension. And I can do this by printing iris data.shape. And this will show me the overall shape of the data set, which essentially means how many rows and columns there are. As we can see, there are 150 rows and 5 columns. These 5 columns consist of these different petal and sepal measurements, as well as the species. And there are 150 different flowers that have been indexed in this data set. So I think that's pretty good to know. So we kind of know the overall makeup of the data set, but I think we want to get it down a little bit further into, I want to figure out how many different types of each flower are in this data set. Is it earlier, like where I had 3 oranges for 5 apples? Are we having a little bit more even distribution? Of course, it's going to be larger numbers because this is a much larger data set than my 8 or 9 image data set, but we'll be printing out iris data describe, and this is just going to kind of show the breakdown. So as we can see here, we're seeing like the averages of all of these different characteristics in the data set. We're seeing the number, the count of everything, the mean, the standard deviation, the minimum value we're seeing for each of these characteristics, as well as the value we're seeing at the 25th percentile, the 50th percentile, the 75th percentile, and the maximum value. So I think this gives us a pretty good idea of the overall value distribution. But if we want to look more specifically into how many types of each species we have, we'll do something like this, which is print iris data, and then we're going to group by specifically the species. And what I want to see is the size. So this will essentially group the data by species, and then it's going to show us the size variable of each of the species like values in the data set. Now, as you can see here, that each of these species and the data set are equally composed. They're all made up by 50 instances of each particular flower, which I think is very good because it gives us a very even indication of these different flowers. If they are kind of like equally as difficult to distinguish from each other, I think this would be a good thing. I think it's going to lead to a very high kind of accuracy rate in our problem. or in our model. So I think this is all very good information to have. So now that we have this, I think we want to have some just some like data visualization, so we can see this a little bit more visually versus just printing out the different information. And we're going to do this in our next, oh, I just made an extra block by accident. My bad. The next thing we'll do after that is move on to the next code block where we'll add some data visualizations. I might add a few more blocks after this just for data visualization to kind of break up those graphs. But this is where it's going to be starting at this comment. So the first thing to kind of show you how graphing will work, we're going to be working on something that we already know, which is the different classes. I think we'll get a little bit more specific and say species breakdown. And for this one, I think we're just going to do a standard bar chart just because it's pretty simple and I'll show you how to interact with our data visualization libraries in this Jupyter notebook. So we're going to be accessing the species column in our data set, and we're going to be counting each of these values. So it's going to be counting each of the unique values and how many times it occurs. So it'll be counting all of these. It'll come to pretty boring bar graph, but I just want to show you kind of like how you would go about creating this. And then I will click plot. So we're plotting this bar chart. And then I will select bar just so it knows what type of chart to do. And then I'll do a title that's just does not need quotation marks there. It does here for our actual title. We'll just do distribution of classes, flower, do even more specific, iris species. We will run this. All right. What is the error we're getting? Okay. X and height. Interesting. Oh, I see what I did. So it's expecting to have 2 arguments in the plot, like parentheses, but the plot does not need to have a parentheses to call that. We're just calling the attribute of that, so we're able to access this bar chart. We're going to run it one more time, and as you can see, here we have our visualization. It's pretty boring, but now you have an idea of how you'll create visualizations in Google Colab. So now that we've done that, I think we need to move on to visualizing the different kind of like numeric distributions of odd sepal lengths and widths, as well as the same thing for the petals. This we're going to do with box plots, just as like a bar chart. And we'll also be doing this like with just like matplotlib code. If you're familiar with Python, it's done the same way as you would in a normal Python file, just within our Google Colab file. So in this instance, I'm going to set the kind of chart to a box plot. And I do want to have subplots because in this particular graph, I'm going to have the distribution of all 4 of our numeric characteristics. So this chart is going to have all 4 of those. Okay, so now that we've taken care of making sure our subplots are there, the next thing I want to do is go to the layout. And we're going to do a 2 by 2 because there are 4 different characteristics. This will allow us to just have a basic square for like this graph image. A lot of the stuff for Matplotlib is just kind of tinkering around with the colors and kind of the overall composition and styling of the chart, but the actual data you're putting into the chart is pretty simple. to kind of walk through that. The next thing I want to do is share X is going to be equal to false, and share Y is also going to be equal to false, because I just want the information on each of these variables rather than plotting them against each other. We'll get a little bit more into that in a few other of the visualizations. For this one, we don't need it. So here, I'm just going to click the play button once more. All right. We have another error. Invalid syntax. Oh, I added a question mark somewhere. At share Y. Let me look through this line and see what I did wrong. Oh, I see what I did. I made this into a variable versus just adding this information into this specific iris data plot. So we'll run this again. And as you can see, it's running. It has the information on the different axes. And these box plots are interesting because it shows the maximum, the minimum, the 50 percentile, as well as the 25th and 75th in a very visual manner, which I think is really helpful when we're kind of investigating our data set before we build our model. I think this is all good information to know when we're building out our model, as well as so we kind of like have a good understanding of what to expect when we get back our results. So I think this is really good to see. And as we can see, some of them are more not evenly distributed. So I'd say that sepal length, sepal width are pretty well distributed. And then petal length is not quite, or sepal width is not great distributed. I meant petal width. My bad. Petal length is relatively good, well distributed, but the 50th percentile is a little bit high in comparison to 75th and 25th. As you can kind of see, it's more even for sepal length and sepal width, as well as petal width is not quite as even, but more so. But sepal width does have quite a few outliers, which are those dots you see at the ends of that box plot. All right, so the next thing I'm going to do is work on a histogram. This will show us more information specifically on the length and the width, but it'll be a little bit just like more information on the specific values versus just like the numbers of how many are at a certain level. Do iris data, and we'll do plot.show. All right, and as you can see, we have these distributions here, and it's showing how many we have at the different lengths. We're seeing a pretty good distribution for sepal, more, I guess, of a bell curve it's following, whereas petal is a little bit more with a spike in the beginning and subsequent spikes. This is also just some good information to know. But the next thing after that is I think we want to graph these different variables against each other so we can have a little bit of a better idea of the relationship in like the different variables to each other, which will be important when our model is figuring out how to how to use those different variables in combination to find patterns. So I will make one more code block. And here we'll be making our scatter plot. This one is going to look a lot larger. The code isn't too complicated because Seaborn does a lot of the heavy lifting, but I'll spend a little bit more time kind of explaining what's going on so you have more of an idea. So we'll use SNS, which is essentially just calling on the Seaborn library. And I'll do set. I'll make the style into ticks. This is just like more of styling with this particular graph. And then we'll do SNS pair plot, which is their verbiage for a scatter plot. We'll be using our iris data. And then for the hue, I want to base that on species. So it's easier for us to distinguish the variables from the different iris species. I will click play. It's running through this information. Okay, and as you can see, the areas where it just follows more of like a line chart versus an actual scatter plot, this is where a variable has been plotted against itself. So on the top left-hand corner, like at the very top, it's because sepal length centimeters has been plotted against sepal length centimeters. So that's like why that happens. And that'll happen just kind of going along, as you can see in the middle, for all four variables. But as you can see, we'll find some relationships to the different variables by species. Different species types with their colors are on the left. We'll see iris setosa, iris versicolor, and iris virginica. Virginica is green, versicolor is orange, and setosa is blue. So I'm going to dive first into the sepal width in centimeters by the length, so that we can see as the sepal length increases, we start to see that iris virginica is occurring more frequently, but also kind of like in the middle, we see a little bit of both virginica and versicolor, kind of in the middle of sepal length. But another pattern I see here is that flowers that have a shorter sepal length, but maybe a little bit of a higher sepal width, tend to be iris setosa. This is more separated from the versicolor and virginica. As you can see in like a lot of these different plots, iris versicolor and iris virginica are a lot more similar than it is to iris setosa. Some of the relationships are a little bit more pronounced, but I think that's a commonality you can kind of see in almost all of these plots, if not all. I'd say that the closest to would probably be these two visualizations. I think they're the closest to the other block, but the orange and green block tend to be kind of more intertwined across the board. I'm going to kind of dive into a few other relationships. I won't spend a ton of time on this. We can get into model building. This is the last visualization we have before model building. But I'm going to do a little bit on petal for each of them as well. And then we can kind of dive into building out that model and how you will go about that using our scikit-learn library. So in petal length, you can see for setosa, it tends to have a much lower petal length and kind of like a low sepal length as well. But we're seeing a much higher petal length for setosa, or not setosa, versicolor and virginica. And as we kind of go along for petal length, we can see that for petal width, we're also seeing that that's larger for our versicolor and virginica. And for setosa, it's smaller. The only thing that I'm seeing as like kind of across the board as larger for setosa is going to be the sepal width tends to be a little bit wider. And we also see, no, I guess that's actually it. Looking at the graph, we're just seeing that the sepal width is wider for setosa, but all three of the other variables tend to be kind of in line with versicolor and virginica, if not much smaller. And I think I want to go back to my slides really quick, just so I can kind of show you those pictures and we can look at like how those numbers translate to those particular images. So this is the image I had up earlier. So as we can see, for the iris setosa, everything except for like that sepal length is going to be smaller. The flower tends to be a little bit more compacted versus the versicolor and virginica, where it tends to be a more expansive flower, and also kind of the width of the like more extending features of the flower tend to be like not as wide. So that's interesting to see, kind of like how that image translates to the like physical measurements in a more empirical sense. Okay. So now that we have a little bit of the measurements compared to those specific statistics, we're going to dive into a little bit more of building the actual model. So the first thing we need to do is kind of segment our data, see the makeup of our different characteristics, and then we'll split it off into like our training and testing variables. We will move down to the building model box. Before I dive into this, I had more boxes for data visualizations, but we didn't end up using them. So we'll just scroll down a little bit. So now that we've kind of gone through and found some relationships in our data set, the next thing we want to do is like work on separating everything out. So the first thing we're going to do is create our X variable. So we're going to go to iris data, and for X, we're just going to have iris data, but we're going to drop off species. And this is because these are all of the variables that we want the model to be finding commonalities based off of. So similarly to how we dropped off the ID because it wasn't useful in that instance, we're dropping it off here because these are the characteristics we want the computer to kind of like find commonalities in and really pay attention to. And the Y variable is just going to be the species. So this is what we're going to have it be comparing all of these characteristics against. So this is allowing it to find patterns a little bit more easily. We're very kind of plainly showing it what things it needs to be paying attention to for patterns versus what the outcome will be. So that's kind of like how we'll be plugging it into more of that like traditional X and Y formula. So now that we have those two, we're going to be calling in the train test split aspect of our scikit-learn library. As you can see here, we imported this earlier from the scikit-learn model selection. So I will be calling that right now. So I'm going to have X underscore train, X underscore test, and then Y underscore train, Y underscore test. And then, so all of these variables will be set equal to something that are generated from this particular call. So train test split, not train test test. You don't need to test it twice initially. And what we're going to be calling in this particular function is the X variable, which is all of that information, like all those characteristics, kind of like the solution or what we'll be mapping it to. And for the test size, we're going to set that equal to 0.2. So this is automatically going to set aside 20% of our data set specifically for testing purposes. So we don't need to manually do that. It'll do it for us. So we're able to go through and kind of segment the data this way. And as far as our random state, we will set this equal to 7, and I will explain that in a little bit. But I'm going to first run it. Okay, we don't have any errors. So that's all looking good. So after this, I wanted to kind of look at the different shapes of our training and testing data segmentations. So I'll be printing off a lot of things. Oh, don't need to be copying in that path. Oh no, I don't need the, thank you, okay. Here we go. So it'll be a very similar call for all 4 of these print statements. It's just going to be the X train and X, the train and test for X and Y. And we're specifically going to be calling on the shape. And then we'll have what? X test dot shape. Then we'll have Y test shape, as well as Y train dot shape. So as you can see, we have everything like the number of rows and columns in each of these different segmentations. And the reason that there isn't like a number of columns in the Y characteristic is because of the fact that we only have that one value, whereas it's 4 and these 2 because there are those 4 different characteristics. And as we can see, there are 150 items. It's going to split it into an 80-20 split. We see that 80% set aside for training is 120, and the 20% set aside for testing is 30 different flowers. I probably should have had Y train ahead of time and then Y test secondly, just to make this a little bit easier to read. Awesome. So now we have a little bit of a better idea of kind of the distribution of training and testing. Our data has been segmented, and we have kind of like all the logistics set up for building our model. Before I dive into actually building our model and all of that, I'm going to check for questions real quick. All right. Someone's taking a stats class right now, so this is perfect timing. Love to hear that. I love to kind of like apply what I'm learning in classes to a project. So hopefully this is doing that for you. You're able to kind of apply the stats you're learning into applied statistics, which is machine learning and a lot of other things in day-to-day life. Do you have any recommendations of resources that cover the math needed for data science, but only the essentials? Yes, I have a few resources at the end that kind of go more in depth with the math behind machine learning, but it teaches you kind of like alongside the practical aspects of coding the models, as well as like how you translate the different mathematical formulas into the concepts and the models. I didn't have a super heavy math background before I started learning machine learning. And the class I took at university on machine learning was aimed towards people that didn't come from like a heavy math background. So my professor did a pretty good job of showing us the formula, giving us kind of like a brief understanding of that, and then diving into how to apply it. He was more concerned about kind of making sure that we understood the concepts of the model versus like super deep into the math, which I thought was kind of like the perfect blend. I'll show you kind of the resources that we used like in that class, as well as like I have used on my own to kind of like learn more about that at the end. But I really enjoyed kind of like how it balances the two, because I do think you need like a solid amount of math for machine learning. But if you are more interested in machine learning than math, you'd like to do, I guess, like a more ML heavy approach versus the theory of math. I hope that answers your question, and I'll show those resources towards the end. What was random state set to? That was set to 7. And that's in the code. If you go to just like the bit.ly I sent earlier, it should be auto updating, as Google will autosave. If it's not, let me know in the chat and I can share a new link at the end of the stream with kind of like the completed code. But I hope that answers everyone's questions. I hope y'all are doing okay, following along with everything. It's like a lot of information the first time you're kind of going through understanding these data sets and building your first model. And I hope that you're able to understand this material. All right. So now that we have this train and test split, we have the shapes. We're going to be needing to import a few more libraries so we're able to actually build out these models. And the first thing we will need to import are a ton of scikit learn models. I don't know if we'll be actually using all of these throughout throughout the live stream, but these will definitely more than cover everything that we'll be diving into. And kind of like a note for like Google Colab is that you'll need to click the play button on the top if you add in any import statements before you run anything else. So if you were to just copy that in but not hit the play button to run all of these import statements, it's not going to update the libraries you'll need later on. So just make sure you do that. For all these libraries you need to import, I'd recommend just going to the bit.ly link again so you can copy all that in, as it is quite a few amount of libraries. These are all scikit-learn libraries. Some are from like different models. Some are like following different testing attributes, and some are for more analysis purposes. All right. So hopefully y'all were able to import those different things. We're just past the halfway point, so I think we need to start with model building. So the first thing I'm going to do is start with building out our models array. So we'll just have this models, like making an empty array. And I want to essentially just add on some different models into this different array so we can run a few different things in this classification model. So I'm going to append this particular model into the models array of LR, which is short for logistic regression. And I'm going to set the solver equal to lib linear. I'm going to set multi-class equal to just auto, so it's automatically finding these different classifications in this model. And then I also want to be able to run a linear discriminant analysis in this model as well. So we'll do that by similarly just models.append, and we'll be doing LDA for linear discriminant analysis, and we'll just be calling that. All right, so we will run this. All right. I see what the issue is. I want to run this entire thing. I need to have a few more parentheses. It was viewing it as 2 items versus just the one. So I want this entire model to be added to this. So this is starting our model. So we have both the typical logistic regression as well as the determinant analysis. And these are kind of like building a few different models. So we have more information to train everything. So now that we have like added those two linear models into our models array, we want to kind of see how like it's all working out. I want to see how this model is running. And we're going to do this by testing it out. So the first thing that I'm going to do for that is print out model accuracy, so we know what we're looking for. The next thing we're going to do is we don't need to print anything else yet. I'm going to make a names array, and also going to make an accuracy array. And for we're going to run a k-fold like validation to evaluate each model. And we're going to call onto one of the libraries we imported earlier. We'll do tenfold. And then we're going to print out the results, which will be equal to score. I will explain this in a bit. Xtrain, train. All right. So what this is essentially doing is for each name that's in this particular model, and for each of the models in the model array, it's going to go through and run a validation to kind of like evaluate that model. The cross-validation score is going to run that testing of the model. And we're going to kind of input the model as well as the X and Y training, and we're going to see how well it's being kind of like trained. And then after that, we're going to move into some more like the results of this and more information on it. So I'm going to add in different names of models, as well as just like more information on it. And then after that, we want to add in the accuracy of each of our models. We'll do that by accuracy.append with our CV. And then we want to change our message to have just the name of our model as well as what the results were. So like the mean, the standard deviation of this model, and see how well we're doing. We need to make any edits to our model. And is it kind of hitting like that benchmark? The benchmark for a successful model is usually around 90%, as you know that you're kind of like on track with a good model. Kind of the overall standard, depending on where you are, is a 95% accuracy rate. And a really good model would be something with like a 99% accuracy rate. So we will adjust this so that it has some information. This is going to have our accuracy and our standard deviation. This is essentially codifying how it's going to print out in our message. And then I'm going to add on the name, so the actual name of the model, the results for the cross-validation, but we want to specifically do mean, and then the cross-validation results for the standard deviation. All right, I think that is everything we need to add into the message. So after we've added on each name and accuracy of all our models, we want to kind of print out our message to see how the different models are running. All right, we have our first error. All right, it looks like I made a mistake. It needs to be n splits instead of just n. A lot of times we'll just be using n when we're calling these libraries. So that's why I made that mistake. All right, so as we can see, the model accuracy for our logistic regression here is 96%, so that's really good. And as we can see, the accuracy for our linear discriminant analysis is 97.5, so we're doing pretty good overall here. I would say that this is a pretty successful linear regression, as well as our discriminant analysis. So I think we're doing pretty well. All right. So as far as like testing more specifically on our model to get information on like the different variables, how accurately it's predicting the different variables, we want to like make more of a function and dive a little bit deeper into our different variables to make sure that it is accurately predicting these different species of flowers. So for that, we need to make a more specified, more specific testing function. So we will create a function, and we're going to add in the model as a whole for our input. We'll do model.fit, and we're going to input our y and x training variables. So we're going to see kind of like the fit of everything by training it first in this testing model, and we're able to access kind of like what it's training afterwards within this function. And after that, we want to add all of the predictions of our model for our testing variables. So this is predicting on the entire testing set. It's making predictions based off of that. So now we're going to print off quite a few things. That should be enough. I can make a few more in a second if needed though. So for our accuracy, we're going to have this first one. So it's going to show, let's do it this way. We'll have the accuracy score for our y variable, and it's going to be based off of the predictions. So we're using kind of the testing answer against our predictions to see how well it's making those predictions. And the next thing we're going to do is we're going to print out our confusion matrix. So this is just essentially how well it's going through and predicting everything, like what the model is confused on. And we can do that right here by calling the confusion matrix library, and we'll do our y-test against our predictions. So again, this is just seeing how much it's getting confused, basically. And then I'm going to comment these out just so we can start to, or we still need to add a few more things. Never mind. So after that, confusion matrix, the next thing we want to do is just start classification report to see how frequently it's classifying each species in this. So we're going to have our classification report, and then I'll have the classification report library, and we'll have what we're getting as our testing solutions against what the model is actually predicting. And then here I will just delete these two because I made a few too many extras. Okay, it says that confusion matrix is not defined. So I guess that I did not import that up above. I will fix that now. Pretty quickly, we'll just do from scikit-learn dot metrics import classification report, and then we'll do the same for the confusion matrix. We'll run this again just to make sure all of our libraries are up to date. And then we will scroll down and run our function. So now our function has been defined, but a function is no good unless you actually call it. So that's something we need to do now. In order to call it, I'll make one more block just so things don't get any more confusing than they need to be. So for the two items in our models array, which is only going to be like 2 in this specific one, but in the future, if you're calling linear and nonlinear machine learning models alongside each other, or you just have like a lot of models running at once to kind of test different things, or you're training the computer to recognize different things, that's when this would really come into play. It would be not too bad if you had to kind of do this manually if you only have 2 models, but it's always good to have code that is kind of like repeatable and scalable. So I'm going to put a star here so we can kind of have a separation between the 2 different aspects of this. And then we'll have another kind of like label so we know what's going on, testing. And then we're just going to have the name so we know like what specifically we're testing. And then we're going to run our function with the specific model so we can get all that good information about how well our model is running and do we need to make any edits to it. All right, so it looks like our model is running pretty well, or our function is running pretty well. I would honestly just change more about how I'm formatting this report overall, the actual model. So here I'm going to add a space just because the lack of space between testing and the model name is a little irritating to me. But as we can see here, the logistic regression accuracy is an 80%. So it looks like it isn't as high as the accuracy we found up here. I'm curious what that is from, but we can investigate that down here with the more details we have from the classification report. So as we can see here, it is accurately predicting everything for Setosa, and then for Versicolor and Virginica, it's having a little bit more trouble. So Versicolor, it's correctly predicting about 88% of the time. In Virginica, it's predicting 67% of the time. The reason for Versicolor and Virginica not being accurately predicted 100% of the time, like Setosa, is likely just due to the fact that there's more overlap between them, so it's a little bit more difficult and will take more data and a more well-refined model for this to kind of like find the differences between those two a little bit easier. As we can see, there's a few places we have errors with these two, but I think that overall we're doing pretty good. With this model, it's not as accurate as our other model that is following our discriminant analysis. So this is just like two different types of models. As we can see that in this particular instance, it's remembering, it's having a higher precision with Virginica, and it's accurately predicting Setosa and versicolor 100% of the time, which is great because of the overlap between versicolor and Virginica. With variables, they're not as clear cut as the difference between Setosa and the other two. So that's what leads to the higher accuracy rating. So I think this is really interesting to see. And it kind of gives us like more insight into what particularly we need to focus on. If we had a decent amount of more time, I would go back and fix kind of the model and adjust it more for versicolor and Virginica. Maybe would add maybe a 90-10 split for testing versus training, or find a larger data set that has more than 150 variables. That's what I would focus my energy on for this particular model. I think that the discriminant analysis, it's running at like a 97% accuracy. I think that we're doing quite well for this model. So I would leave that one kind of like how it is, unless we need it to be 99% for some very specific use case. But I think overall, we're doing a really good job with this model. So that's all I have as far as training and testing the model. Do we have any questions? I know I kind of threw a lot of information at you, and I want to allow you to ask any questions you might have before I dive into some of the resources that y'all can use to continue learning after this workshop, more about kind of like the math theory, as well as like more like machine learning. All right. I'm not seeing any questions, so I'm going to go back to my slides. So now that we've kind of gone through the iris, like the classification model, I've shown you how to kind of look through a data set, how to build out that simple model, and how to go through and test it. I'm going to walk you through some resources that I think are super helpful for learning more about machine learning, learning more about the math behind it, and kind of building out more projects. So the first is Kaggle, or the last one is Kaggle, but that's what we kind of like went into earlier. So I'm going to talk a little bit more about it. Kaggle is a great site because not only does it have like a lot of data sets that you can use for your different your different projects, you're able to kind of like learn different types of models and like about different types of problems that you're interested in through Kaggle. They also have competitions where, similar to hackathons, you can focus in and hone your skills in like kind of a short period of time. And they also have a lot of places where you can answer questions. So I'm going to switch back to Kaggle. As you can see, we have all this information on like the iris use. There's like information on the downloads of it being data site, but there's also discussion here where you can kind of like talk about different aspects of the data set. I think that if you go through, you can look at the beginner's guide to an iris data set. I use this when I was first learning about machine learning. They walk you through a bunch of different information on how to build out those models. In this case, how to like do data visualization. Looks like they did some similar things to us, some different visualizations, some bivariate analysis. Okay, something similar to us. We did not do this one. All right, they did a little bit different of a model, but some similar aspects as well. So this is pretty cool. You get to see kind of someone else's approach to the same data set or similar problems. If you look in discussion as well, in addition to like the more tutorial-y things, you'll have list of kernels, updating different imports for specific notebooks they might have, um, for different questions you might have. So if you like have a specific question, you could leave it here. Looks like no one answered this question, so have to find something else to walk you through. Different questions you can walk through and kind of like talk about with people, in addition to different code. So you're able to walk through different notebooks and people's approaches to maybe a different model or classification you have going on, maybe different projects they worked on in addition that maybe use this and like build upon it to something else. If you go to competitions, you can see different competitions that are going on. Some we can like use for like prizes or just like learning, I think is the most useful aspect. But I think the biggest part of Kaggle is using data sets, because you're able to find like a large amount of information that you need to collect and use it for learning more about machine learning. But kind of diving back into the other resources, the Google Cloud Machine Learning Engineering course, I found to be a pretty cool resource. I have not completed it myself, like fully. I've gone through and read a lot of the articles and labs in here, but they have kind of an intro to a lot of different machine learning tools and information, with like just a lot of insights that kind of like pair the math with the overall kind of like practicalities of machine learning. They're very long, and they provide you with some cool information and projects if you want to do this at like a more kind of like extended pace. And then in addition to that, I would also recommend deeplearning.ai. This is a really cool resource that was made by a machine learning professor. This is a resource that I used quite often in my machine learning class at university. My professor really liked like the short courses, the diagrams that they had in here to kind of supplement what he was teaching us in class. So if you go through, you can filter for kind of your level. Say that most people in this class are a beginner, and you're able to go through and find different things. A lot of these are about LLMs, which are pretty popular in machine learning now. But if you scroll down, you can find some more kind of like basic machine learning and deep learning classes. I believe so. There should be like the basic course here. Yes, the machine learning course, the machine learning specialization is what we focused on in my like intro to ML class. So I think like that's a great resource to use, as well as the deep learning specialization is kind of like a building off of this as well. They have like a lot of helpful videos, GitHub repositories, and also just like information on like new kind of like up and coming things that are happening within the subfield of machine learning. All right. So those are all the resources that I have for like learning more about machine learning, learning more about like the math behind it. Hopefully it can help you pair what you're learning in maybe a statistics class or a math class with how you can apply it in machine learning. But that's all I have for y'all today. Thank you so much for attending. If you want to go back and look at my slides or pull up that Google Colab like Jupyter Notebooks file, you can go to this bit.ly link. It's bit.ly/GHW213. And if anyone has any questions, feel free to drop them in the chat. I'm going to be going through now and looking and see if I missed any. Do you think a random forest model would perform better for this data set or clustering? I do think that clustering Might have been maybe a better approach versus the model that I had made. For this, I like kind of like retrospectively, with it being like category based, and that could have performed better. In the future, I'll go in and kind of like look through that to see how it performs, and we can kind of use the precision data and kind of compare how those two would compare, or how the precision of those two models would compare. But yeah, we have a few people saying thank you so much for coming, everyone. I hope you had a good time and learned something, and I hope to see you throughout the rest of Global Hack Week, and I hope you learn a ton about machine learning throughout this great Global Hack Week. Thanks for coming out. And again, if you want to go check out the code we walked through or the slides, you can head to this bit.ly link, which is bit.ly/GHW213. All right. It looks like we don't have any more questions, so I'll be heading out for today, but I'll see y'all around in the Discord and later on throughout the week. Thank you so much again.